Hello, ladies and gentlemen. First of all, a very good morning to you. So, first of all, thank you for the organizer and host for providing a great opportunity. And first of all, so our paper that is accepted title is Stride Randomizing Augmentations. So, I am myself Teerath Kumar, a PhD student from the Ireland, Dublin University. So, first of all, the content, the agenda of our presentations, as you can see there. First of all, I'll give the introduction, brief introduction, what augmentation is and why we need it, and then the motivation of the problem, that what problem actually, what are the limitations of the previous augmentations, and then we'll go to the proposed solution, that what we propose, and then I'll describe the few contributions, and then I'll move toward the algorithm that we have provided, and the experimental sections in which we will talk about the results and like say experiment setting stuff like that, and then finally we'll talk about the conclude our work, that what we have done. Okay, so first of all, so let's say introductions. As you all know that deep learning algorithms are the data hungry. They require a lot of data and to give like the desired accuracy. But the data is very limited, and deep learning algorithm, more importantly, deep learning algorithm require labeled data. you know and for the label data, it is very difficult, and like to label the data, it's very expensive, tedious task, and very time consuming task. So if the data is very limited, then the model can be lead to the overfitting. Basically is during the training, model may give you will give very good performance on the training data set. However, on the test data set, it will give you very less performance. So model is more biased over the training data. To cope up with these issues, to reduce the gap of these limitations, the data augmentation was used to to give a regularization effect. You can assume, say, let's say when we are child at the age of 5 years, let's say first time when you see the dog, once you see the dog, next time when you dog comes, it's very difficult to recognize. And when you see the dog like multiple times, different let's say you see the white color dog, red color dog, and multiple color dog, and when next time any dog comes, you recognize. Why? Because now you our mind has recognized the very important features, and for that it's a kind of data augmentation. Data augmentation is basically increasing the data to give one kind of regulation effect. And so coming to the motivation, so as I already described the data augmentation, so I'll move to the specific kind of data augmentation, that is random erasing. Random erasing is a data augmentation basically in which the random region of the image is erased, and then it passed to the deep learning model. Here you can see that in random erasing, the problem is that, let's say we take any picture, and when we randomly crop this and pass to the image, as a human, let's say if you see the image that is cropped, you see the white color box, oh sorry, black color box. As a human, you cannot recognize, say that either it's dog, either it's cats, you cannot recognize. The problem is that when we pass this image to the model, the model cannot recognize, because as a human we cannot recognize, then how model can learn? So this is the basic limitations. As you see dog image, that on which we apply the random erasing, then as a human you ask the question yourself, is this a dog? So we cannot say anything, right? So this is basically motivation of the problem. And another thing is that, let's say the region that is erased in the dog label, so still we pass label of this image as a dog. So but model, so it can misguide the model, because the most important features that has already been erased by the random erasing. So what we propose that we provide stride augmentation. Stride is basically kind of a straight line with a specific size and that we propose to deal with random erasing issues. uh, while in the random erasing, in the random erasing, basically the label were not given label were not like smooth, label were not assigned a percentage. Like if in that you can see that when we merge the 50% of dog, 50% of cat, you can see that in the like in the augmented image, dog is 75% and cat is 0.2% of the image. Because if you see in the cat region, if you see only upper part, in the like cat half stride or been like overlapped by the dog, overtaken by the dog, you can say so. And at the same time the label are also smooth. Label means the dog, let's say dog percentage in this image is 75%, and cat is percentage is 0.25 percentage. So that is we call stride raising, and that we act in the deep learning we named is like stride random raising data augmentation. All right. So this is basically a contribution of our paper. We propose a very novel, unique kind of data augmentation that we name as random stride random raising augmentation to address the random raising limitations. Second, we perform many experiments on the wide variety of student data sets using our proposed approach. We investigate the effect of stride size. Stride size means here you can see that the cat like cat stride size is not fixed. Like cat stride, like it randomly changes, and we tried multiple experiment. Like we tried the stride size very small, and we tried the stride very big, and we tried the stride size randomly in a specific range. And we also check the effect of different augmentation probability. Let's say augmentation probability means like what are the chances that stride augmentation will be performed. It's not about the mixing of those two images, it's about how much percentage that like data augmentation will be performed, like our stride random raising augmentation will be performed, right? So, and so like lastly, like finally we like propose, like we release our code that is publicly available on this GitHub repository, and so that the future researcher can explore it further. Right, this is the contribution, and this is the algorithm. Basically what we do in algorithm we get one image, another image, and label of image one, label of image two. As you can see, the input that are parameter that are coming into the function, and what output is augmented like image and augmented label. We generate randomly probability, like random probability of mixing x2. That, let's say, for you can assume that what is the probability of mixing the cat here you can. And stride size means how much like stride that should be fixed, and based on the probability that we have like got the probability of mixing two, like we say the how many stride of that, like based on the probability, how many strides of the image two should be taken. And then more importantly, start position, the stride from which like portion of the image stride should be like mixed, like taken. So for that we like take the number of stride, we provide a loop, and then we slice, like we slice the image to the index slicing, and then we get xi image that we define variable here, and finally we divide the probability half two, because the interval that are moving with us last like with interval of two, that's why we divided by probability by two. And here are so coming to the experiments, the experiment we use to check the effectiveness of our like proposed approach. We use the data set like including grayscale and color scale, and also for the diversity purpose we included the number of classes like with a different variety. And we also seen the data set that are that has very few number of images in the training and very large number of the images in training, and also we check the performance based on that is the basic states that you can see the of the data sets that we use in our experiments. You can see the probability that effect of probability, like how much chances, basically probability here says that probability of performing the stride augmentation vs test accuracy on the fashion amnesty data set using resonate 20 net. So here you can see the probability. Let's say we change the probability, we give the 0.1 probability of performing the stride random augmentation using the fashion amnesty resonate. You can see the accuracy that's around 90, and here you can see the maximum accuracy that we got. It gives 0.5% probability give maximum accuracy, and we use that for the all the experiments that we use, because it is just a hyperparameter, so we pick the best one. And secondly, stride size. Stride size, as you saw in the like as I previously told that we investigated a different stride size. When we use stride size very small, very thin, then it was like giving like probably performance test accuracy of 90 around like 94, near to 94. But when we use random stride each time during the training with each epoch, when the random stride like randomly generate the stride size, its accuracy boosted very importantly, very largely, because always randomness always works the better. And in a large stride size, its accuracy further drop. So we use in our experiment stride size as a random, right? That's the effect of the stride size, how it changed. And then like previously I was told, in the we use the probability best parameter as a 0.5, and we use the random stride as a best hyperparameter. So here we have compared the performance using the different models of the Resonate VG16 with, and we report the error rate. So in a baseline, you can see in the first like Resonate 20 in the fashion image data set, baseline result is 6.21. I forgot to tell that each experiment is repeated at least 3 times, so that we can say that the results are generated are very good results. In the Resonate 20, you can see the baseline has a 6.21 error rate, while in random raising it was 5.004. While in stride random raising, it gave the error rate that is further reduced, that is better. So you can say 4.9. In this way, if you look at the overall picture of the stride random raising, it gave a very impressive performance, and it gave very competitive performance in a few cases as compared to random raising. So these were two data sets on which we performed, and there are two other data sets we have performed the results. You can see here the C400, and you can see STL10, and you can see the results. The results are very good, and even it outperformed in a few cases with a very large, with very like high percentage, especially in the cases of VGG flavors. So there was the experimental results section. And so to conclude our paper, so we address the problem of the random raising. That's like in random raising, it sometimes lose very good features, as I showed in the motivations. There like it like lose very good features that like discard the models, and it deteriorates the performance of the model. So to deal these issues, we propose new data augmentations. We named it stride random augmentations, random raising data augmentations. And furthermore, we investigated the hyperparameter of proposed augmentations, namely probability of performing the mixing the two images and the stride random raising. And furthermore, to check the effectiveness of the performance, like we performed the wide variety of the experiments on the different data sets using different network flavors of the networks, including Resonate and VG. And so we now our like future work is to extend our work by including column-wise augmentation. Now, for the time being, we are just performing the augmentation on the row-wise augmentation. To further affect the effect of the column-wise augmentation, and to check the row-wise and column-wise augmentation, and furthermore, we will also check our proposed augmentations on the other domain data. For the time being, we have just checked the our augmentations in only image domain. Now in the future, we'll move to the audio domain. So that's it. Thank you.